At Context Free, we talk about programming languages. And one thing I enjoy is WebAssembly. And I've been doing a little bit of learning more about the details myself recently. And I enjoy awesome web demos like these from Ben Smith, such as this ray tracing here, where the Wasm itself comes in at under 1.5K. The UI library for these controls is much larger. And here we see there's also not a lot of support code in the web page. It calls into the WebAssembly, or Wasm, at each frame, and then updates the pixels on the canvas. You can dig through the source code as well in the WebAssembly text, or WAT format. And this is what we'll be looking at today, because working directly in binary Wasm is much more difficult, and WAT and Wasm translate back and forth between each other rather easily. In addition to example programs here, or example output from compilers, you can also look at the WebAssembly specification, which includes a spec for the text format. Mixing all that together and asking a few questions is how I got through a lot of what I did. One reason you might care about understanding Wasm is so you can produce better Wasm from whatever programming language, or because you want to compile your own language to Wasm. So let's look at some code. Here we have a very simple WAT program. We import a print function, which receives a single integer, which will be the memory address, and we export memory, which is an array, and we also export the main function, which calls print twice with two different strings, where I invented my own string layout format. I have one string at address 0, another at address 16, where I have a little Indian number for the length of the string, followed by the text data. So let's try running this. And we see hi there and bye y'all. We can also increase the length of this string and add another bang on the end. Very good. And I'm running this using bun through a script that I wrote called wasmini, which first loads up the specified Wasm file, then instantiates an app from it, and then calls it, where I'm expecting these two members to be on my app, which are the exports from my WAT file. To instantiate the app, I created an environment, including forward references to variables I haven't defined yet, because you can do that in JavaScript, as long as these aren't used until after they've been defined. I return my exports, and instead of my print function, I look at the length of the string, then I decode UTF-8 so I can print it out. To run it, we convert the WAT to Wasm, then bun run my little script with the name of the Wasm file. Now let's do something a bit more complicated, which is Fibonacci numbers. Here I've got a Zig program, which has an obscure way to loop n times, and for each time through the loop, I'll print out a Fibonacci number. I could have called this function directly, but instead I'm going through a different version that puts a value on the stack and then calls the fib function to update that value on my stack. I did this because I found that I needed to know how to use pointers to stack variables, and it wasn't obvious in WAT. So I wrote the Zig program to see how Zig compiled to Wasm for me, where I can get the Wasm out and then use Wasm to WAT to get it back into WAT format. So example how you can use other programming languages and compilers to help you understand how WAT works. But just to prove what the Zig program does, here we've got Fibonacci numbers 0 through 34, or indices 0 through 9. Anyway, let's look at the WAT implementation. And I wrote this mostly by hand, though again referencing other code out there. And instead of using my simple environment with my simple print function, I'm instead using the Wasi fdwrite function. So I can run this program from a Wasm engine that knows Wasi, where Wasi is the WebAssembly system interface, which gives you access to a lot of POSIX functions. In this case, we're using fdwrite, which is very similar to this writev function from sysuio.h. We give a file descriptor, a pointer to iovec structs, and the number of structs that are in there. Each iovec struct has a pointer to the memory you want to write in this case, and the length of that memory. Notice this is far more complicated than my simple print function that I had here. And in fact, in the Wasi version, instead of returning back the number of written bytes, you have a pointer to where you want that to be at, and a separate return value, which is an error code. Also in Wasi, your main is called _start. So here I loop up through value 9, and continuing the loop if we're still less than or equal to that value. Now notice all these I32s here in WAT. These are unspecified for whether they're signed or unsigned. It's the operations themselves with S for signed or U for unsigned for how things work. And I may have been a bit sloppy throughout this in which things I made signed or unsigned, so you might need to forgive me in that. And I also defined my own expectations of where my stack is going to be. I had my stack start at 1K and growing down. So I only have 1K of memory for my stack. Better be careful for that. And there's two separate stacks here in Wasm. One is the stack of the function calls, but you can't get pointers to any of those local variables. You have to maintain a separate manual stack if you want pointers to local variables. And that's what this is for. And I mean pointers such as things like RIOVEX or the number of bytes we've written. So for my Fibonacci number calculation, I do recursive calls with helper identifiers here to make it easy to call your functions. These just become numbers in the Wasm. And Wasm is a stack machine. So I push a value on a stack, then I check it. Though they have this convenient stuff here, which basically pushes these on the stack in order, then calls this operator. But I didn't find any such convenient syntax for if. That's why I'm pushing it in advance manually here. And any particular expression here can have a value. So I said, this if else has result type i32, just like the function itself does. And before we get further, let's actually run this. Where here I'm converting my Wat to Wasm, and then I'm running this Wasm with Wasmer. And I get the same output as in Zig. You can also see the size of the output Wasm file at 480 bytes, with no further post-processing or optimization run in this case, though there are options for that out there. And just to point out how the stack stuff works, I can change this implementation so that instead of using this local variable to return, I just use the expression value of my outer if-else directly. So we shouldn't need this local result anymore. And we can instead just use the value 0 for the 0 case. Let's see if I did this right. Looks like I did. And our Wasm file is now only 472 bytes. Worth pointing out that Wasm is a very efficient binary format. You should expect to see Wasm files that are much smaller than your Wat source. So here I made a convenience print function, which acts like the print function that I had implemented directly in my Wasmini. But to do this, it has to push things onto my manual stack, then call the fdwrite that I've imported, and then put the stack the way it was before. And then beyond that, there's nothing built into Wasm for formatting integers. I possibly could have found a third-party implementation, but instead I implemented my own print function for printing signed integers to standard out, where, for example, I put in a negative for a negative number, then I count the number of bytes I need, and then loop all through again to put out those bytes in reverse order, because it's easiest to grab off your smallest digits, but you want them on the end instead of on the beginning of your string. So it gets tricky. Then I call my own print function, and I get rid also of my local handy-dandy stack space where I was building the string in question. Luckily, I know the maximum size for a 32-bit integer, so I know how much stack space to reserve. Here's my stack pop and push helpers, and here are my hard-coded strings in the format expected by my own print function I defined, where I insert formatted integers in those missing slots. And notice that I put these after my manually chosen stack start. Finally, I did look some at Wasm binary for a simpler program, and I went byte by byte through to figure out what each of those bytes was doing. Fun exercise, but definitely took a lot of effort. And Wasm to Wat can give you a little bit of helpers with these things to describe where certain parts of your code are at, and again to convert your Wasm back into Wat to see what's going on. So anyway, before I go, I also want to point out the Roland language, which I've mentioned before. Richard has a great page up here with example Hello World and Fibonacci number programs, which calculates a Fibonacci number for you, for example, for number 9, which gets the same 34 I get here, and prints that out. And what's cool about Roland is that it's actually running the Roland compiler as Wasm inside of the web page. There's no server involved here. You can also disassemble the Wasm to Wat here as well, just right in page. So it's an easy way to explore programs and see what they compile to right from your browser. Anyway, I hope this has been fun. Maybe we can dig a little bit more into Wasm in the future. Bye, y'all.